All right, how's it going, everybody? We are here on Wednesday. We're going to look at a little bit of section 6.4 today. We're going to talk about work, physics section here. Um, and man, before I get started, I literally feel like I would be a crazy person if I did not directly document what it looks outside, like outside my window right now. So I'm going to slowly turn my screen and just doesn't look as impressive from the little computer monitor here, but man, it is just straight up dark out. My kid's just been sleeping all day because he thinks it's nighttime. Uh, Man, it is crazy out right now. I hope that the fires are not directly affecting any of us. I hope that the people in Willits are doing all right, and I hope that this does not come any further north. Because holy cow, it looks like the apocalypse out there. I hope none of you had travel plans to go south anytime soon because you can't. So what a weird looking day. I just can't stop looking out the window. I feel like I went to undergrad in Colorado and grad school in Montana, and then taught again in Colorado. And I knew as a student in Colorado and as a professor in Colorado, the most annoying thing as a professor is on the snow days, everybody's just like looking out the window the whole time as it's snowing. I'm like, hey, I'm up here. And it's hard to get. I feel like that's like the version of what's happening outside right now. It's like I can't stop looking out the window. Um, and and since I brought it up, there's a bunch of pictures of the Humboldt sky on the internet right now. I've also been seeing a ton of pictures of, since I mentioned it, where I taught previously in Colorado, because they actually have a snow day today. So also, if you want to think about crazy things in the sky right now, uh, imagine having a snow day from school in a town that always gets snow and never has snow days on September 9th. It's a mountain of snow right now in Colorado, which is pretty funny. Um, I guess that would be better than a fire. Yeah, it looks like Mars out there. I agree completely. It's that like I don't even know if it's the true color of the surface, but all sci-fi things have taught me that this color orange is like, I feel like Crayola would name this crayon Mars orange. Like that's what the sky looks like right now. Um, Wild. I'm just gonna be staring at the sky the whole rest of the day. I love the fact that I have this gigantic window sitting in front of me right here, so I have a nice clean shot of this. So yeah, it'd be nice if it didn't look like this, but oh, yeah, I guess you're right. Yeah, I guess it is combustion that makes it look orange there as well. So, yeah, it's physics, right? Hey, there we go. Nice lead into the day right there. There we go. So it's physics that's actually causing this. So today we're going to talk about work, and we are talking about work in the physics sense here for this section here. So we want to make sure that we understand what we mean when we talk about work. In this section here, this is one of those ones that I feel like I occasionally struggle with because I always have some students that are like, I'm a physics student, like I'm taking calculus because I need it for physics. I'm going to be an engineer, blah blah blah. And then I have other students that are like, I'm a math major. I am not trying to be a physics major. I took that class. I'm not a physics major for a reason. This is for everybody. If you're a math person and if you don't think of yourself as a physics person, everybody needs to be a units person, and units is what this is going to be kind of guiding us here today in our words. So we want to let units and words really be some help to us today. So the good news about today is that aside from as this whole section, the integration that we're going to do in this section isn't going to be too terribly difficult. Setting up the integrals as usual is going to be kind of difficult. The formulas that are associated with a lot of these physics equations, though, are incredibly easy. They're literally a single multiplication, like simpler than even y equals mx plus b. It's more like just y equals mx is all that we're dealing with for a lot of our equations here. In fact, all three of our directly applicable equations today are of the form y equals mx. So that's nice. So that's hopefully your starting like comfort zone right there that you're going to be able to at least do some multiplication meaningfully today. And so I don't know that there's ever been a time that I've ever taught anything physics related. And I should actually, let me back up one quick second again and say I was really nervous the first time that I realized that I was sort of expected to like teach physics basically because So like when I was an undergrad, I wanted to minor in physics to go with my math major. But the school that I was at is a small enough school that they only offered. I know that you guys know about some of these problems. They only offered like each physics class. Like I could only take one physics class per semester, and it was going to be. I was a transfer student to that college, and so it was going to take me like 6 semesters to take 6 physics classes. Where I was comfortable taking them more often than that, but they were prerequisites for each other and all that, and there was no way for me to finish it in time. So I never ended up pursuing the physics path, but I think I took 2 or 3 semesters of college physics classes. And I think of myself as a physics oriented guy, but I feel intimidated by a lot of things in physics because it's so much more about the broadest version of problem solving that there is rather than applications of formulas. It really matters that you're a thinker to set up a bunch of this stuff. And so it is what I like to think that I'm good at, but also when I present it to students, it's some of the most like I don't know. I don't really get too nervous, but like this is these are the things that I'm like, okay, like did I really say that right? Did I set that up right? Are my units correct? Did I place my origin at the smartest possible place? Is that I these are the problems that I always imagine there being a physics professor like looking through my door, just shaking his head at me, and I picture Eric Kramer all the time. For those of you who have taken physics classes with Eric or are going to, and I always picture in a positive, constructive way him like passing judgment on me. And so I always try to kind of keep my things in line. And really, Calc 3 and differential equations are much more physics oriented classes than this one is. This is like one section of this class right here. But Calc 3 and Diffie-Q are like it's those classes might as well be called "What math do you need to know to be good at physics?" And so those are much more heavily physics oriented, and I those topics are all awesome that are covered in those classes. I love all the physics stuff that we do in Diffie-Q, which by the way you can see a mention of on the screen right now. So stick with this. This is really interesting. This is hard in a different way than a lot of the other stuff in this class is hard. A lot of the stuff in this class is hard because integration is hard and because sequences and series are hard. That's like the two big difficulties of this class. This is a different version of things being hard right here. And so I don't know. If you aren't excited about this section, I would encourage you to try to change your mind real quick because this is really cool. This helps make a lot of calculations happen that otherwise we only have access to the absolute most simple type of calculations that don't describe meaningful situations. And now adding integration into these ideas is going to allow us to actually do meaningful physics computations for honestly kind of the first time in your life right now. So this will be really cool. I'll tell you a good story about that later that'll make all of you upset. So every time I ever talk ever about physics, the very first thing that ever goes on the board for every physics problem in the history of doing physics for me as a calculus professor is F equals ma. Force equals mass times acceleration. This is Newton's second law of motion. I don't know why it's second. It should be first. I don't even remember what the ordering of all three of them are. But in any event, force equals mass times acceleration. This is how we verbalize it. F equals ma is a crazy easy equation. It's a multiplication of two values to get a force. But what you should notice is that F equals ma is actually a differential equation because acceleration is the second derivative of position over time. So a lot of equations that we will build in differential equations next semester, because I know all of you are going to come take it with me because that's what you should do because it's the best class that you can possibly take with all of your calculus knowledge, is we're going to start a dozen problems in like a 2 week period of time with F equals ma. We're going to build from there. This is going to describe all the forces impacts on a certain mass associated with its acceleration here. So F equals ma. Pretty rare to find yourself in physics scenarios in which that's not relevant. Okay, that's a too broad of a statement right there. But for my calculus purposes, man, this is where it's at right here. So we'll build off of F equals ma as one of our baseline equations for the day right here. So of our non-calculus equations that we're getting for the day, this is one of our like 3 key ones right here. And I think it's something that even if you've never directly handled it, I'm pretty sure that everybody in this class has heard the expression force equals mass times acceleration at some point in their life here, and we're going to deal with it a little bit today. So what we're really interested in talking about, though, is work. Work is defined to be a force applied over a distance. And the immediate thing that we want to do is separate in our minds the generic word work from the physics word work. Work is things that you think of as like going to a job. It's obviously not that because this is physics. Work you could then think is okay, so it has to do with applying a force. So like if I try really hard physically to do something, then that should constitute work because I'm burning calories at least. Well, that's not even quite true either. Work has to be a force that is applied over a distance. If the distance that the effort is applied over is zero, then the work done is also zero, despite the fact that you may have completely exhausted your body. So I always say, whenever I'm talking about work, if you push against a wall as hard as you can for hours, you have done zero work because the wall never moved. The distance was zero, so I don't care if the force is a trillion that you've applied to the wall. That is being multiplied by a distance of zero, and therefore there are 0 joules of work that have been performed. We're going to talk units in a minute. I'll come back to that in a second, but work units are typically given in joules. So remember that work is not even just like effort amount. Like I just said a second ago, if I pushed on a wall as hard as I could for hours, I'm going to burn a ton of calories. That is going to take effort from me, certainly on my part, even though the wall doesn't move. But if it doesn't move, then no work was done, right? Work is force times distance. So you should immediately be pretty happy that the two of the three most important equations of the day look like they do. It's not going to get a whole lot, like, could we state simpler equations than this? I literally don't think so. Force is mass times acceleration. Work is force times distance here. And you should notice that if we want to compute work, it seems like we need to know the force that's being applied. And if we want to know the force that's being applied, it seems that we can compute the force by determining what the mass times the relevant acceleration would be in that situation. So let's use these two super simple equations to compute a really simple example just to get started. If you've never done a single physics computation before, then here you go. Here's going to be our nice easy one. I'm always picking out the things that are relevant to me in my life. How much work do I perform when I pick up my child? He weighs 10 kilograms, and I need to lift him about 1.6 meters. I'm about 2 meters tall. I'm a little under 2 meters tall, and I usually carry him pretty high, maybe 1.5 meters more appropriate, whatever, doesn't matter. I'm kind of making up numbers here anyway. You should notice that one of the important things here is that I am choosing kilograms and meters. That is because I am an educated person and because you are also an educated person and working on being an educated person. You should also force yourself into metric all the time. Okay, here we go. There's going to be a couple Tony stories here today, so deal with it. One of my close friends from undergrad and from grad school, we actually went to both undergrad and grad school together. He feels exactly like I do. He loves it when I say the things like I just said, where because we're educated people, we will use metric. One of the unfortunate things about metric is people don't have a good of like sense of intuition about it, right? And so like in math, like we always want to have intuition. If you were to tell me something's 20 feet away, I can picture that. But if you were to tell me something's 20 meters away, it's a lot harder for me to picture that, obviously, because we don't work with those units as much. So what my friend decided during undergrad that he wanted to do was like try his hardest to like familiarize himself with metric by like saying things out loud. And so there was a winter, and we lived in one of the literal top 5 coldest places in the country. And every morning when he would wake up, he would walk out onto his front porch in his boxers, stretch his arms, and he had mounted a thermometer to like the wooden post that was sitting on his porch. And he would lean in and he'd be like, right now, it is 4 degrees Celsius outside. And he would sort of announce it to the world. And he would try to do that all the time so that he could normalize himself with some metric measurements. Because again, temperature is one of those things where if you tell me it's 20 degrees Celsius outside, I literally don't know like how to dress for the day. It's not clear to me what temperature. I have to sit and do some calculations. I don't have a feel for it. So be a metric person. This takes time to get comfortable being in units of measurement, and educated people don't do things in standard. So be a metric person. So here we are. Our book, by the way, is going to do some things in standard, and it bothers me immensely. For your take home, for your by hand homework for the week, I am putting all of the units in metric and telling you to change the conversion that the textbook references for you to put it in metric, because that's the way that smart people should do things. So be a metric person. There's Tony's story number 1 for the day. So let's go ahead and look at this problem here. So when I am picking up my child, what I am doing is I am resisting the force of gravity, right? That's the force that I have to overcome to lift him off of the ground. So my little diagram, because there should be a diagram that goes with every single physics situation here. Oop, my legs are a little small there. Okay. Hey, my stick figures are looking pretty dang good right there. That's pretty dang proportional. So what I'm noticing here is that the force that I need to apply is a upward force, and the force is resisting gravity, right? So gravity is really the force that I'm fighting against here. If there was no gravity, then we wouldn't have any weight. We would only have mass, right? So I am resisting that force of gravity based on that direction of motion here. So what I want to do is I want to determine the work, and I know that work is force times distance. And I know that this distance I've already been given, it's 1.6 meters, but what I don't know is the force that's being applied. So I can at least right now say I know that the distance is 1.6 meters. And I'm going to keep units, I'm going to try and do a good job with units today. We're going to get a little lost in, we're not going to get lost, but we're going to end up in a situation where there's too many units for me to meaningfully do math and follow units at the same time at the end. So I want to do them here. To understand the force, I need to know that force is computed by mass times acceleration. I'm writing this as mass times acceleration rather than just m and a because I don't want to confuse mass m with meters m right there. So make sure that if you're ever dealing with those collectively, lowercase m is very typically our meters notation here, since we should be working in metric here. So what I need to know is what is the mass that I'm moving and what is the acceleration that I am providing. I know that gravity moves at 9.8 meters per second squared down. Therefore, to resist this, I need to apply a force of 9.8 meters per second up so that I have completely negated that force, that downward force that we're experiencing here. So it seems to me like the mass associated with this is 10 kilograms. It seems to me that the acceleration, this is a negative 9.8 meters because that's the force of gravity, negative 9.8 meters per second squared. I, therefore, am applying a positive 9.8 meters per second squared in order to lift my child here. So 9.8 meters per second squared. I am going to do that force based on that acceleration against gravity for a total of 1.6 meters. So let's see what we end up with here. If I do this multiplication here, the slightly unfortunate thing is I have kilograms, I have meters on top, and I have more meters on top. These meters aren't even canceling. I have second squared on bottom. There's no other second squared. There's no unit canceling that's happening in this whole dang thing, which is, I always love unit cancellation. It's one of those things that makes me really happy. I whenever I'm doing my like y equals mx plus b, I always show people this is like dollars equals, dollars per hour times hours plus the initial number of dollars that you had, and hours and hours cancel, and you get dollars plus dollars equals dollars. These are the satisfactions that I am interested in finding by way of units here. Like that's what I do in my algebra class. We're just going to have a lot more hairier units here today, but that's okay because we're all mathematical adults here. So it looks like I just need to multiply these three numbers together here. So I'm going to get a 98 times 1.6, and I'm getting 156.8. So 156.8. And it looks like our units are kilogram meters squared per second squared. And I guess this kind of makes sense. The meter squared is a tough interpretation, but kilogram meters is just saying that there's a weight moved over a distance right there. This is the units that we're going to come to call joules right here. 156.8 joules. And let's talk about our units right now. So this example right here, obviously no calculus just happened right there. The really important thing for us to realize is that we have a whole bunch of words that we want to be able to use here, and it's totally cool for you to use actual words rather than individual letters. Don't get lost. This is just an organizational based section for sure with all of our units and stuff. So work was force times distance. force was mass times acceleration. So it seems like in this case, it was useful for us to compute work as mass times acceleration times distance. Seemed to be, in this case, the appropriate way for us to compute a work amount right here. We'll see that we'll get some alternate representations of that, but they should all lead us to the same units that we get down here. And this is the definition of a joule. Now, because a joule is a metric unit, you should expect it to have an incredibly nice verbal definition, and it does. 1 joule is the work required to produce 1 watt of power for 1 second. All the metric stuff has all these awesome sentences that have the word one in them everywhere. And that, even if I don't quite understand what things like 1 watt of power are, the sentence still makes me feel comfortable that a joule is a sensibly defined quantity right here. So I hope that this sentence gives you some light amount of comfort right there. All right. So a joule is a unit of work, and it's the amount of work that is required to produce 1 watt of power for a second. Joules, as we just saw, have units of kilogram meters squared per second squared, but we can also write this as just a Newton meter. So it should be, hopefully we can see that if I'm trying to say that these two things are the same, I could sort of, in a sense, cancel this 2 right here. I don't want to overwrite it, and cancel this m right here. So it seems like 1 Newton is a kilogram meter per second squared. And I can see this just because if a Newton times a meter is the same thing as a kilogram times a meter squared per second squared, I, in a sense, just divided both sides by meter, and I arrived at what 1 Newton must be. But then we should say, well, what the heck's a Newton? Well, Newton, since it's a metric quantity, it has a nice sentence that includes lots of the number 1 in it. 1 Newton is the force required to accelerate 1 kilogram of mass by 1 meter per second squared in the direction of the force. And again, that statement, I don't like, it's not like I care that you guys memorize these statements or anything. Like, obviously you could look them up if you needed. Every time I make one of these metric statements, this just provides me some like level of comfortability that it's not like the stupidest relationship of all time, like we have between feet and miles and inches and pounds and grams and ounces, and the fact that ounces are both a weight and a volume. And like, oh my gosh, whoever's responsible for assembling standard measurements is one of the worst people that's ever lived. It drives me insane. So it bothers me that we don't live in exclusively a metric situation. We would lose nothing and gain everything from doing that, but we don't. So again, if you're an educated person, then you should do your infinitesimally small contribution to moving our country in the direction of converting to metric. Okay, let's start some calculus. So here's our issue. All right, this work equals force times distance is a true equation, but unfortunately this equation is not actually helpful to us if our force changes over time. If the force is constant the entire time, as gravity is for me, then we can just go ahead and include that force as just a number that's in there. But what if the force changes as the object moves? What if the distance that the object has been moved alters how much force we're applying? I think of pushing a person on a swing, because when I think of pushing a person on a swing, when the person's very close to you, you have a lot more pushing power and you push very hard. But when your arms are like almost all the way extended, you have a lot less pushing power. Because the distance has changed, the force that you're applying is getting weaker and weaker and weaker over time until you give that final little push of the fingers there, and then you're applying no force, right? So we go from most force to least force as we push a person on a swing. The force is changing over time, so there's not like a number that I could give for force. The force is dependent on the extension of my arm, in a sense, right? If my hands are up against my chest, I would consider this 0 distance pushed, and then this would be full distance pushed hopefully I don't lock my elbows and injure myself as I'm pushing a person on a swing like I just did with my arms there. But right, we can imagine that force might change as the object gets further away from us. Or I like to imagine every time that my child does not recognize that like a cardboard box is perhaps empty, and he'll walk up to it to like lean against it, but then we'll just collapse to the ground. He's pushing on the box, but then eventually he's not pushing on the box anymore because he's just fallen to the ground in front of the box right there. So hopefully it makes a obviously huge amount of sense to you that we don't just apply constant forces all the time. That when you apply a force, you move something, and because you moved it, the amount of force that you're now applying to it might be different than it was before it moved. In this case, we just want to be able to give a whole function of force, right? And hopefully, again, that makes a bit of sense right here. F of x, the force should be determined based on how much motion has already been accrued right there, how much distance we've already pushed, x, right? So if we want to accrue force over a distance, then we can subdivide all of our distances into a Riemann short distance, an infinitely short distance. And so we can think about sort of discretizing this as to say, okay, right here as I push on the swing, I'm applying a lot of force. I'm going to do that for, 1/1000th of a millimeter. And then I'm going to recalculate what my new force is. I'm going to push that force for my 1/1000th of a millimeter. And then I'm going to recalculate the new force because my arms are a little bit more extended. I'm very slightly weaker here than I was here, right? And so this is our integration. We are making infinitely small changes and recalculating the force at every single infinitely small distance change. We're accruing all of those forces times distances over the distance from x equals a to x equals b. This will give us our integral that will compute work for us rather than just a direct computation. The good news is that this works for all sorts of forces, right? This doesn't have to be about just one specific thing. We did force based on acceleration due to gravity a second ago. And in a minute, we'll get force that is based on, excuse me, we're going to talk about a spring force. We could talk about gravitational force. All of these are forces, and the good news is that this work equation is going to work the same. As long as you have an equation for the force, you should be able to hopefully perform the integration necessary to determine the work that is being done by that force being applied over a distance. And again, the force might be changing. This brings us to our second Tony story of the day, a brief story about computing specific heat. So as I just told you guys, like I've taken a decent amount of physics, and when I was in high school, I took 2 years of honors physics. I was part of the robotics team and all that good stuff. But the problem with taking physics in high school is that no physics class in high school ever has the expectation that the students in the class already know calculus. And hopefully we're all relatively aware that literally physics was invented just to help us do, excuse me, calculus was invented just to help us do physics. Like they are intertwined in an incredibly deep way. But in high school, most physics students haven't taken calculus, right? And especially like I took physics my junior year, like you couldn't have even taken calculus until your senior year. And so all of the physics computations all have to have some sort of linear version of them where we're not actually doing any derivatives or integrals that would technically otherwise be appropriate. This is a perfect example of what you're already looking at on the screen. I absolutely did sections on work in high school, and it was all work equals F times D. Then when I got to college, work became the integral of f dx, right? That's the difference that we're doing right there. So let me tell you the story about this. So I've always been an academic student that's a bad student. Let's put it that way. I've always been a school-oriented person. I've always enjoyed school. I've always appreciated the challenge of school. I have always enjoyed my hard classes. My hardest classes are usually my favorite classes. But I'm also a lazy piece of crap most of the time. And I try to end up getting away with doing less. Now I'll just tangent this again off of my tangent here. When I took calculus, when I was taking honors calculus, my senior year of high school, we took 4 total tests over the course of the year. There were 2 tests in the fall and 2 tests in the spring. And 2 of those tests were pretty easy, right? Like when you first learn calculus and you're learning about like limits, like that stuff is pretty easy. But then when you get into things like integration, it gets pretty hard, right? So out of the 4 tests in my honors calculus class, I got the best grade in the class on the 2 hard tests of the year, and I got not the best grade in the class on the 2 easy tests of the year. And the reason is because all of my friends needed help for the hard stuff, and they were like, Tony, you got to help us study with this. We can't figure any of this stuff out. So I would have to help them do all the work, and because I did the work in helping them, I learned it better, and then I crushed everybody on the test. On the easy test, nobody needed my help, and nobody asked me for help, and so I did no work, and so I did mediocre on the tests. So I like to have the challenge that's out there, but also like if you don't challenge me, then I'll sort of just sit there like a lump. This brings me to college. So now I'm in my junior year of college and I'm taking some physics classes. I started going to school at St. Louis University. They have an incredibly good aerospace engineering program there. And sort of what that means is nobody goes and takes physics classes just to see if they maybe want to do physics classes. Like it'll kick your ass. And so So I was discouraged from sort of exploratorily taking a physics class because I was at a school that had a very competitive physics program. And so when I transferred to my college in Colorado during my junior year, they had, not a intensely competitive physics program, and so I felt a lot more comfortable with the idea of taking some physics classes in a sense, sort of like just for fun. As I said, I kind of wanted to physics minor, but I figured out that it wasn't going to be reasonable within my time span there. So I go to take this physics class. I'm taking like a 200 level physics class, and it ends up being the case that we're covering like a ton of topics that I had covered when I was in high school. The only difference was is that in high school there was no calculus in all the formulas. Now there's calculus in all the formulas. But because I'm a lazy piece of crap, I'm like, I've seen this before, even though I had done none of the math. I had the concepts, but also like, man, I'm talking about junior year of high school to junior year of college, right? So there's like a 4 year gap between when I first learned an alternate version and when I was next expected to know the upgraded version. So because I was a horrible student and had, I was doing a few things other than going to class during a bunch of undergrad, it turned out that I somehow decided that it was going to be acceptable for me to not go to physics class for 2 full weeks. I don't think I like planned that, but it sort of happened that way. It was a Tuesday, Thursday class, and so I no-showed Tuesday, I no-showed Thursday, I no-showed Tuesday, I no-showed Thursday, and then I showed up to class the next Tuesday. And when I walked into class, everybody's sitting there like frantically tearing through their notes, and I knew like all the people in the class. There were a bunch of math people in there. Like I was buddies with more than half the people that were in there. The professor was a pretty funny guy. He joked with us all a bunch. um, and I kind of walked in and I was like, oh crap, well, what's up? And all my friends just looked up at me being like, you idiot, there's a test today and I know that you don't know about it, because they all knew that I hadn't been in class. There's only like 15 of us in the class anyway, and so they all were like, ha. And I was like, oh my goodness, okay, well, I guess I'm taking a test today. We had covered like two entire chapters since I had last attended class. But I kind of like sat there and I was like, I could bust out my textbook and try and study real quick, but I was like, no, this is like a Zen moment. This is a moment where I need to just like become one with earth and physics and calculus and just see if I can just make something happen here. One of the major parts of the test was discussing specific heat. And you should be thinking about like how much heat can an object hold. Aluminum foil is terrible at holding heat. Water is excellent at holding heat. We want to be able to we want to be able to calculate like temperature changes over time dependent on the specific heat of an object. So what happened on this test was that like I saw a bunch of words that I recognized from 4 years ago in a physics class. And because I'm a total loser that memorizes tons of things sort of by accident and never forgets them, I still kind of remembered like most of my formulas from high school. And so I was sitting there in despair, and it was when the professor came around, when Dustin came around handing out the test. He's walking around the class handing out the test to everybody. And when he got to me, he like sort of did the motion of like sort of chucking it at me, and then he stopped and he just stared at me, and he like stared at me and just smiled at me, and then just dropped it on my desk and walked away because he knew I was screwed. All my classmates knew I was screwed. Um, and so I'm looking at test question number one, and I'm like, okay, apparently I missed stuff about specific heat. This is good. I know about this stuff. And I'm sitting there in my head, and I'm like, all right. I remember in high school there was some formula like what did we do in high school? I think it was something like Q equals MC delta T, where the C is the specific heat of the thing and the Q is the accumulated temperature change over the time delta T. And I was like, I don't know. I mean, I guess if I'm doing this now in calculus class, that this should just be something like Q equals the integral of MC dt from like time zero to time final, I guess. And so I basically just like remembered a bunch of formulas that looked like this, wrapped them all up in integrals and switched the deltas to d's, and on that 5 question test, I actually ended up getting a 100%, much to the intense dismay of my fellow classmates and to the entertainment of the professor, who was very confused as to how I actually did that, having never been in class for the sections. But the point is, it's like that to me was sort of like an enlightening moment for like doing calculus, where I was like, oh my gosh, like you really can just wrap stuff up in integrals and accumulate it over time or accumulate it over distance. And I did it sort of as a guess because my other option was just to take a 0 on a test. And it turned out that I literally nailed it. And so the only 100% I ever got on a test in college was on a physics test that I didn't even know was happening that day. And so I still well, laugh with my friends about that one, although they don't laugh very much about that. They're still mad at me about that one today. Um, so the point here is, if you've taken physics before, then you already know all the stuff you need to know. Wrap some things up in integrals, change your deltas to d's. We're integrating. So here we go. By the way, also, here's some physics that doesn't require F equals ma right there. That was immediately what I thought of when I said that. That was probably wrong up top. So what I'm going to suggest to you right now, rather than me spending my time doing a crazy easy example that's in the book in example 2 does a very basic initial computation with this equation right here. They literally just say the force is like this, like some polynomial function, and what's the work that it takes to push the object from 3 meters to 5 meters. And it's just the integral from 3 to 5 of the polynomial. There's nothing that's super fancy about what's happening right there. We've got a force and we've got a distance over which we're applying that force, and it's going to give us work on the other end. So I'm going to skip that. You can easily go read that example that's right there. What I want to do is I want to do some slightly harder examples, and so we're going to do one slightly harder example with discussing spring force, a different force that we haven't talked about yet, and then we'll do an example that's supposed to be kind of helping you think about the by hand homework for this week, this second problem in the by hand homework here. So, Hooke's law. Hooke was a physicist. He's the guy that formalized the statements that we make about spring forces. The force required to maintain a spring stretched x units beyond its natural length is proportional to x. That is the verbal version of Hooke's law. I can write this as an equation. This says to me, so in general, I just always write a force as an F. And this is like habits that I've developed from teaching differential equations. The subscript of S here is telling me that this is a spring force. So I'm just saying in this statement here, the force associated with a spring being maintained at x units away is proportional to that distance x right there. Whenever we're talking about a proportion, that means that there should be a constant of proportionality that's associated with it. So when I say it is proportional to x, that's not an equal sign. I can convert the proportionality symbol into an equal symbol by just explicitly identifying some constant of proportionality, k. One second, please. So any proportionality statement right there just means there is a constant of proportionality, some unknown constant coefficient. So in this expression here, k is the spring force constant, and x is going to be the distance that that spring is being maintained at. Now, just as we were talking about before, all these physics equations are easy if things are constant. If we are holding a spring a constant stretched distance, then all we have to know is k times x. If we want to do the stretching, then what you should imagine to yourself is that at first it's easy to stretch a spring, but the further and further you go, the harder it gets because it's already been stretched more. So what you should imagine is that this is a perfect integration situation. We should imagine we stretch the spring that 1/1000th of a millimeter right there, and then we recalculate the new force, and we do another 1/1000th of a millimeter, and we recalculate the new force. That's just called integration right there. That's exactly what we're doing. That 1/1000th of a millimeter, that's our infinitely thin Riemann stick right there. So again, you should be happy. Our third key equation for the day is also just a multiplication of two numbers. So that's really nice for us. So the book does a very nice example where they importantly highlight the difference between maintaining a spring at a distance and stretching a spring at a distance. To maintain a spring at a distance is a constant distance, therefore it has a constant force, therefore you can just do force equals k times x. K is just the spring constant for that given spring. The spring constant should always remain the same unless you damage the spring, stretch it beyond its stretching capacity, whatever that may be. And you should imagine that things like a slinky has a very, 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 very small K. It requires very little force to stretch that spring. On the other hand, I remember in high school, my physics teacher literally brought in shocks from his car. It's a spring, but it's a spring that's supposed to literally hold the weight of your car. It's if two people press on it as hard as they can, you can barely see a shock from a vehicle move more than like a quarter of an inch. So it has a massive K value, huge values for difficult to stretch springs, tiny K values for easy to stretch springs. So again, I think it's example, let me just look so I can directly reference these things. Yeah, in example 3, the book highlights this difference between maintaining versus stretching. Maintaining, constant force, do multiplication. Stretching, force is always changing, so we need to do integration to accumulate all of the infinitely small pieces of sort of like linear constant force along the way. So what I'm going to do here is let's go ahead and take a look at some of the, oh, I didn't even, oh, okay, it's like I didn't even type it out. Let's go ahead and look at, we're going to do 2 book examples here for our work examples here. We're going to do 1 spring example, and then we'll, again, do 1 example that's intended to kind of help guide you in your thoughts about the take-home, one of the 2 take-home problems for this week, the by-home problem. Yeah, the by-hand problems. I can't think of my hyphenated words right now. Okay, here we are. So, suppose 2 joules of work are required to stretch a spring from its natural length of 30 centimeters to a length of 42 centimeters. If that's the case, then how much work is needed to stretch it from 35 to 40? So this is one of these cases where there's some unknowns, but as you can notice here, we're not actually computing the work. We've been given the work. It seems like there's some unknown information about the spring that we need to determine so that we can answer this final question right here. All right? So what I know here is that work is going to be the integral of a, oh man, oh, I just committed the ultimate physics sin. As I told you, I always imagine that Eric Kramer is like watching me through the window and judging my every move whenever I teach anything physics related. It helps keep me on my toes. The ultimate physics sin is to not draw a picture first. Always draw a picture first for every physics problem you ever do in literally your whole life. Never don't do it. Great, let's draw a picture. So when I draw my spring pictures, I kind of draw the same picture every time because consistency is good. I am picturing like a mass on a spring, right? And so or not even a mass on a spring, I guess, but we've got some spring sticking out of the wall right here. What we know is that its natural rest position right here is 30. And what I am going to do is I am going to make an axis down here. And I am going to really think of this as 0 right there. I'm going to consider the spring to be at rest when x is equal to 0, right? And so maybe I'll say something like distance equals 30. I'm going to say that corresponds to x equals 0. Again, for those of us that are not well experienced in our physics things, one of the most important things to be good at, one of the like arts of being good at physics, is picking smart places for your origin. You can define a coordinate system any way you want to do your math. I could define this literally an infinite number of different ways and get the same answer every time as long as all of my relationships are appropriate. Picking a smart place for 0 to be defined is one of the most like artistic things about being a good physicist. I feel like it's this thing that's not obvious. It's a thing that there's never like a hard set of rules as to how to do it. It requires intuition. It requires you to say, oh, I remember last time I put it there because it seems smart, but then my integral was crazy. But if I put it there, it seems dumb, but my integral is easy. And it takes time to kind of feel these out. In this case, I think it's very natural in our very basic sort of one-dimensional spring setting to say where the spring is at rest is what we should be considering position 0. We should recognize here that we are therefore interested in some other locations here. So other than 30, we're interested in like 35, 40, and 42. And so these are all distances to me. I am going to refer to these x values then as x equals 0, 5, 10, and 12, because this is the distance stretched from rest. This is the distance from the wall. This is the distance from rest for the spring down here. So I've picked a smart place for me to define my own 0, is the first thing that I did. I drew a picture and I defined my origin. Those are kind of like the standard things that go with every physics problem. Always do those. Those are for you. Those are not for me. That's because this is usually difficult or impossible if you don't do these things. In this case, maybe not, but like, just wait. You need to draw a picture for everything. So, what I know is that work is I know that what's going to happen here with this spring is as I begin to stretch it, it's going to require more and more force for me to continue stretching it because the further we are stretched, the more force is required to stretch it a little bit further. So I think here that I should be able to make some statement that says something like, we're going to go from our natural length, x equals 0, all the way up to 42 right here. Oh, how obnoxious. I was waiting for that to happen. I'm a cool enough streamer now that we're getting spam, guys. How awesome is that? Work equals the integral of, we're going to start at our beginning location, 0. We're going to go to our stretched location, 42 centimeters. We have defined to be 12 centimeters further than our original starting location right here. I know that this work should be the force that is being applied. And the good thing that I know is they actually already told me the answer. They told me that this amount of work is 2. I know it's 2 joules. That is the answer from this. Right? What we're interested in knowing here is how much work is it going to take to go from 35 to 40. So let me even just see what this integral statement means to me. My real question should be, what is the force of interest right here? Maybe I should call this like F sub S right there. So in this case here, my spring force, as we defined a moment ago, is just K times X. But as you should importantly notice, I don't know what the K constant is that's associated with this spring. So apparently the information that they're starting us with is saying, listen, I don't know what this spring force is, but I do know that if you were to stretch it by 12 centimeters from rest, it's going to take you 2 joules. That should be enough information for me to determine what is the spring force constant associated with this particular spring, right? So what I'm going to go ahead and do is I'm going to do the integration, and I'm going to solve this equation for K, because I already know what the output is for my integral. It's 2. Right? So I should be able to solve this equation now for K. Once I know K, K will be used for me to actually compute the desired thing with the work from 35 to 40. So it looks like here, K is just a constant. X has a power of 1. The integration is going to make the x power go to 2. So 1/2 kx squared seems to be the integral that we're going to get out here, evaluated from x equals 0 to x equals 12. And that should be equal to 2. And I'm just going to drop the j for right now so we don't get any confusion of lettering out here. Just a real quick evaluation of this then. It looks like, oh man, awesome polynomial stuff. Evaluate at 0. It's not going to get better than that. So I've got 1 over 2 times k times 12 squared is going to be equal to 2. 12 squared is 144. Half of 144 is 72. Right, so 72k equals 2. And so k is going to be, it looks like 1 over 36. Okay. So what I've done here is I've determined that this is like weaker than a slinky. This has an incredibly weak spring force right here. You don't necessarily shouldn't be able to judge that yet, but if you've done some physics stuff, then you've seen some spring constants of some typical typed springs and stuff like that. I feel like it's a very standard thing in physics lab to like literally compute, like hold this spring in your hand and compute its K value by doing some measurements and stuff like that. So getting that intuition. This is hardly a spring is what I would say right here. So knowing the K value now, I now should be able to actually compute the desired value, the work that is occurring from, and now we're going from 35 to 40. So remember that we're interpreting 35 and 40 as 5 centimeters beyond rest and 10 centimeters beyond rest. So the work that's required to do all of that motion from 5 centimeters to 10 centimeters should just be this force applied over a distance. Right? What distance? From 5 to 10. In this case here then, it looks like we're sitting in a similar situation, but the good news is that kx for our spring force, we actually know k now, right? So it looks like I can actually just write this as k I know is 1/36. So I think that this is going to be my integral that's going to actually get me my work now to get the spring from 35 to 40 centimeters right here. So we're cruising here. We're essentially done with this problem. Let's just do this integral real quick here. I'm getting 1 over 36 times 1/2 x squared, evaluated from 5 to 10. That's going to give me 1/2 times 10 squared minus 5 squared, which is 1 over 72 times 100 minus 25. That's a 75, so what? 75 over 72? Whatever decimal we're going to get out of that guy right there. That actually reduces nicely, doesn't it? 25 over 24. Whatever decimal that is, that's how many joules we're getting out of that. I'm not going to get out my calculator. You guys should probably get decimals instead of fractions for these, but we're all numerical adults here. You can do that step right there. So in this case right here, you should notice, unless we're given a spring force constant, you can't tell me how much force is required to move any given spring. We got to know information about the spring. So they first gave us information about how much work it did take to do one stretching. That allowed us to solve for K. Knowing K allowed us to determine more information about future unknown stretchings. So that's kind of a nice thing here, is that technically speaking, you should only have to stretch a spring one time and measure the force associated with that to understand all future possible forces required for any amounts of stretching for that spring. Once you've done one stretching, you can compute the K value that is associated with it. And by the way, in physics lab, even when I did this physics lab in high school, like we would just set up this equation and solve it here. Like this, we knew it was from rest to some certain distance with some, we had Newton meter, like Newton measuring devices that would measure the total amount of newtons that were being experienced. You can make this computation here. So nothing super crazy. These integrals are pretty dang easy right here, but for the millionth time, like it's all about setting this stuff up, right? And here, I think that the big things are make sure that you're drawing a picture, make sure that you're defining a coordinate system and defining where 0 is located within that coordinate system. That's some really important stuff there. Um, yeah, so force over distance. So this was kind of our easy one. Let's look at a harder one now. A circular swimming pool has a diameter of 24 feet. The sides are 5 feet high, and the water in the pool is 4 feet deep. So this sounds to me like one of those like backyard pools that's like the halfway in between being a crappy pool and being an awesome pool, like the above ground pools right here. It sounds like what this is here. A circular swimming pool is a diameter of 24 feet, sides are 5 feet high, but the water is only 4 feet deep, right? So the water is not like to the brim of the pool. There's still like a foot gap between the top of the water and the top of the pool. What I want to know is like if I have a pump and I need to pump all the water out of the pool, like it's, winter is coming, it's going to freeze, I got to pump all the water out of the pool for the winter. How much work is going to be required? I could potentially use this information to determine even things like if I knew what engine I was using and if I knew the efficiency of that engine, I could probably even determine things like how long do I need to run a motor to pump all the water out of this thing. We don't have that extra information here, but we want to know how many joules of work are required for us to get all the water out. That's our question here. So as I am now not going to forget, I'm going to draw my picture first. Here's my very bad pool. Oh my gosh. Oh my gosh. Hope you don't want to go swimming in this pool here. All right. We've got our water right there. I know that I'm going to go ahead and immediately do this. I know that literally I never care about diameter in my life. Radius is the thing that we always ever care about. I'm just going to immediately convert that information into radius. That's a 12-meter radius or 12-foot radius. Oh, I forgot. We don't get metric units for this one right here. We're going to do this one in standard just so that we can all realize that we hate doing things in terms of feet and pounds. What else we got here? So I know that the water height is 4 feet. I know that the top of the pool is 5 feet, right? So those two numbers are going to play similar, but obviously not identical roles in this problem here, since the water height is not fully the height of the entire thing right here. What else? We got any other measurements here? We've got the weight of water right here. So what we kind of need to think to ourselves is how are we going to accumulate all this stuff right here? Well, what we're going to do is we're going to pick out a Riemann object and we're going to move that one object. We're going to think about dealing with one Riemann object. Then we're going to wrap that Riemann object in an integral and apply that Riemann object's idea to all of the infinitely thin layers of water that we're going to view in this pool. So what I like to picture here is, in fact, by the way, I feel like okay, sure, I'll do that one. Here we go. we should be picturing that there is one Riemann disk of water that's sitting in the pool right here. I should probably use colors more than I do here, huh? So we've got one Riemann disk of water. And what I want to suggest here is that I am going to define now. Remember what I just shouted at you guys a second ago. The two most important things at the beginning of every physics problem is draw a picture and define your coordinate system. In this case here, since I'm thinking of this pool being oriented vertically, I am thinking of a y-axis out here. I am thinking of the bottom of the pool as being y equals 0. And I'm just going to call this generic location, the generic height of this to be just y, right? I'm not identifying. My Riemann disk of water is at height y. So what I'm thinking to myself is that if we're going to come up with a work statement here, work should be a force times a distance. What we want to do is determine the work associated with moving one, I'm picturing one infinitely thin layer of the water. I know that all of the water that is on one layer needs to be raised to the same height so that it can flow over the edge, right? So what I'm picturing is that one Riemann layer of water that is in the galaxy coloration right there. All of that needs to go the same height, whatever it is, right? And by the way, I'm going to ask you what that height is in a second. So you should be thinking, if the height of that Riemann layer is y, what is the height that that layer needs to be raised by to get to the edge? That'll be something that we're going to bring in here. So let's set up that one Riemann disk of water at a height of y, and let's see if we can make some statements about this here. So let me try to reference my... Yeah. So our force, we need to come up with this force times distance stuff right here. And we need to do this for every single layer that is in this pool. So what I need to do is I need to know about force, and what I need to do is I need to know about distance, right? So let's talk about force, and let's talk about distance. Let's talk about force first. In the case that we're talking about force, we need to know what the force is that's going to be required to move all this water. And the good news for us is that we always get to go back with force to our good old friend Newton's second law of motion. Force equals mass times acceleration. So if I want to know the mass of that water, that's going to be a little bit tougher right there, right? Sorry. Where's my, But I feel like I'm dropping a number here and I'm looking at my notes. 1 second here. How did I trick myself here? What am I thinking? Oh, I know what I'm doing. Okay. I see how I've tricked myself here. What happened to me right here is exactly what I've been yelling at you guys about this whole lecture so far, which is be in metric. Here's the issue. Kilograms are mass. Pounds are force. Unfortunately, we interchange those on Earth because on Earth we experience a constant force due to gravity. But unfortunately, pounds and kilograms are actually measuring different things. Pounds is a unit of force, right? Uh, Whereas kilograms is a unit of mass. So if I'm looking for the force here, I am looking for how many pounds do I need to move over a distance. So I'm going to rewrite this is our number of pounds right here. So my question is, how many pounds of water are in our Riemann disk? Well, the good news is that I can compute the volume of the Riemann disk, and I also know the weight of the water per unit of volume, right? That's per foot cubed right there. So that pounds is what I want. I want that little lb right there. That's my key thing. That is my unit of force, a pound. So what I'm thinking to myself here is this force, pounds, this should be our volume. This should be our feet cubed times our pounds per foot cubed, right? This is our volume times our density, right? So if we can come up with the volume of this disk and multiply it by the density that was given to us in the problem, then we'll have the force that's required to be moving this one disk of water, right? So what's the volume of this disk? Well, I've got that our volume is going to be, well, I'm just thinking it's area times thickness, right? Our volume should be pi times the radius squared. Come on, computer, why are you doing this to me? Come on. So here's our area, pi r squared. That's the area of the disk. It has thickness, right? But it's got infinitely thin thickness. This is our Riemann disk. It's our one representative slice, our cross-dimensional slice here. So I'm going to say that our thickness in this case is dy, right? That should be the thickness associated with this slice here. So I think I can say that this is 144 pi dy. This is my total volume of one slice. It's the area of the disk, and its depth is this infinitely thin depth. It's a Riemann disk here. So I'm going to give it a dy, or even just a delta y. The book does a great job of doing the deltas and the sums and converting them into the d's and the integrals out there. I don't. I end up using the infinitesimals quite a bit more here. So it looks like we can compute this then as 144 pi times dy, that's our volume, times this density that we've got. We were given that the density was 62.5. And if you go ahead and multiply that stuff up, what you're going to get is 9,000 pi dy. So it looks like this is the force required to move one Riemann disk. What we need to do is multiply the force times the distance that we need to move that disk, and then we need to add up all of those for all of the representative Riemann disks, right? So keep staying conceptual here. We want to always talk about just one individual Riemann object, then accumulate those Riemann objects by integration. So defining the Riemann object and finding its properties is always our key here. So here I have defined my Riemann disk. I have found the properties associated with my Riemann disk, or not all of them actually, I still need my distance component, but then we can multiply force times distance and accumulate all of that via integration. So the next question here is, what distance is this Riemann disk going to need to get moved? Well, it needs to get to a total height of 5. It's currently at a height of what I am calling y. And notice, if you're on the bottom, we should have to move a grand total of 5 feet. I keep on almost saying meters. At the bottom, we need to go 5 feet to get to the top. At the very top layer, like literally out of the infinite number of Riemann disks stacked up here, there's a topmost layer, and it only needs to go 1 foot to the top up there, right? So what I'm always seeing is I always like to think of my final minus initial. The final height is 5. The initial height is y. So it looks like the distance that we're going to need to be going here, this distance should be 5 minus y. So now that I know what my force terms are and my distance terms are, I want to accumulate all of the forces times distances for all of my Riemann disks. The reason I did this generally in terms of y is because I want something generic that will work for all of the y values of interest to us. Let's note real quickly before I even start writing my integral, what y values are we considering here? We're only moving the water that exists from 0 to 4 feet. We need to move it a total of potentially up to 5 feet distance, but the water being moved starts at height 0 or starts at most a height of 4 right there, all right? So we've built our force, we've built our distance, let's accumulate them with an integral. I just want to keep this on screen here. So our force term, 9,000 pi dy times the distance moved, 5 minus y. I'm noticing that I'm setting up an integral dy, so I'm asking myself, what are the y values that we should be considering here? And again, you should notice that we are never starting water between 4 and 5 feet high. All of the water starts between 0 and 4 feet. Therefore, these are my bounds of integration. The fact that we need to move it a distance of 5 feet is handled by the distance component. The 5 is incorporated in the distance component. The starting locations are all of the bounds of integration for me from 0 to 4. And now that we're here, we're, as I said, every problem I have set up this semester, we're basically done. We've done the hard part. We've gotten to the integral that now represents the quantity of interest. So I can now rearrange this maybe a little bit. I think it might be nicer for me to write this as 9,000 pi integral of 5 minus y dy from 0 to 4. Nice little clean integral there. And now we're just integrating. And there we go. Now we're just evaluating and we're good. Oh my gosh. Are we ever going to get a lower bound that's not 0? Is it ever going to happen? 9 times 12 is 9. What are we going to get here? Oh, I can't do. Is that right? Right? 20 minus 16. Half of 16 is 8. That's 12. 12 times 9 is 108. With 3 more zeros. 108,000 pi. And so I can now do 108,000 times pi. And that's going to tell me 339,292. And I'm going to go ahead and say in these problems also, like, if we're counting hundreds of thousands of joules, then I'm pretty cool with you just chopping all of our decimals right there. If I see this, it's pretty obvious to me that you got to the right ending spot right there. So it appears that this is the number of joules that will be required to move all that water to the top, where it will then flow over the sides. You should notice that it doesn't require force to be moved left or right. When we're moving up or down, we're resisting that force due to gravity, which is where weight comes in. That's the difference between weight and mass. Mass, if we were dealing with a mass there, we would still have to multiply by acceleration due to gravity. Since we were dealing with pounds there, we did not. So again, I want to encourage you to think of this super conceptually. I know that this is how I really think about my work integrals. I literally think about it with actual words being in the integrand. This helps me to say, okay, all I've got to do is come up with the force associated with one Riemann disk and the distance associated with one Riemann disk that it needs to travel, and I can throw those two parts in there. I should also point out to you that I like to think of in these integrals often as like the dx as like the distance that's being traveled. Notice in the spring case here, dx was in the direction of the motion that was being traveled right there, but in a sense, it didn't quite represent, it represented to me the dx was sort of like my distance component. Down here, the distance component wasn't the dy. The distance component was the 5 minus y. It was the overall distance that this thing, each piece needed to end up traveling right there. So, like, it's okay if you have dy's not literally sitting at the end the way that you initially set it up. Dy is a multiplicative term in here like anything else, right? It's just the thickness of our Riemann layer of water right there. But again, I think thinking about these conceptually is a lot easier than just trying to do a computation. When you look at all the work that happens, when I mean work, I mean algebra and calculus that happens in the section in the textbook, this is like the most symbolically heavy section of the entire textbook so far. But I think that this is one of those things that really helps for you to like take a step back and say like, oh, those 19 terms being multiplied, that's just them getting force because they followed their units out and multiplied the right stuff to get force. And so they have a force term right there. That's all that is. And recognizing that maybe big groups of kind of nasty looking terms are really like one simple idea. And so don't read these and get lost and feel like things are too hairy. Realize that lots of these gnarly terms grouped together, 9,000 pi dy, That's a really simple idea. The force required to move one Riemann layer of water 5 minus y units to the top of the pool. When I describe it in words, it's easy, and therefore you should describe it in words too to feel like it is as easy as it is. So the of the two problems that I assigned for the by hand homework for this week, the second one is a very similar problem to this, but it definitely has a couple differences. It has about as many differences I could possibly incorporate into it without it being a totally different problem here. And in particular, one of the things that I'm going to ask you to do in this problem is to do the entire problem generically, meaning I'm not giving you any numbers whatsoever. It's going to be in terms of like the height is A and the water's height is B and the radius is C and the all those types of things. The density is rho and all those types of terms. Gravity is G. So for these things here, think in broad terms. Think in terms of our conceptual integrals rather than trying to think that there's just going to be, like, I don't see this formula from the picture. I don't see this formula from the setup right there. I can't just build this. It requires me to write words and think about what each of those words, how I can build them. And again, I used units. Units were my guide here. I knew I needed my force to be pounds, and I saw that the only place I ever saw pounds was here. And so I thought, well, I do know that 62.5 pounds per foot cubed has pounds in it. So if I could somehow multiply 62.5 by a meaningful volume, a foot cubed measurement, I would have pounds. And so I hunted for pounds in that way. So, there's a lot of physics lessons that go with this section. Draw pictures. Define your coordinate system and where zero is located. Use your units to drive all of your decision making. Your units will never lie to you. If your units are correct, then your answer is correct, always. So trust your units. And if you can't figure out the quantity, all you have to go do is find one unit that has the unit that you desire, one value that has the unit that you desire in it, and you can extract that unit's information by multiplying or dividing by appropriate quantities out there. So like I said, lots of physics lessons that go here, but really these aren't physics lessons. These are math lessons. They just are best seen in a physics setting right here. So it disappoints me that this is the only like major physics section, and that's not the case. We will actually do some other physics things in chapter 8. But again, Calc 3, you'll do more physics. Diffie Q, you'll do more physics, and it's good. I kind of feel like this is not too hard of a section, but I feel like this had the feel of a hard section. I feel like in differential equations, it's hard to make problems not physics problems. It's hard for me to even come up with interpretations for what I've even done mathematically in differential equations if I can't give it the wrapping of a physics problem. So I also just want to say, like, I don't know, for better or for worse, however much you love or hate doing the physics problems, know that doing more of it, you will only like it more. Nobody goes to differential equations and is like, oh, now I really don't like physics. It always makes things easier to do the things that we're doing in the later courses that are slightly more focused on physics concepts out there. So I'm telling you as an honest, good piece of advice, look forward to that. It is the best parts of those courses. It is the whole reason that calculus was ever invented in the first place, was to do physics. So it's the most quintessential way to wrap up the calculus things that we do is in physics concepts here. So that's the things I wanted to do here today. I think the hardest homework problem for the entire week is going to be one that's a lot like the one that you're looking at on the screen right now. As you can see, we should be normal schedule for next week, Monday and Tuesday. For our lectures, we're going to be wrapping up chapter 6. Man, that's an easy one. I almost might, to be honest, drop my window there. So I'm just looking at our schedule here. Yeah, 6571. Integration by parts is going to take some practice. So I'm going to say to you guys, next week I anticipate the video components being short. My Monday video is going to be very short, hopefully the shortest of the entire semester. I think section 6.5 is probably the shortest section of the entire course. 7.1 is maybe the most important integration technique that exists. And as my maybe departing statement to you here, let me show you one quick thing, something that you don't know how to do yet. That's kind of strange that you don't know how to do it yet. and show you one of the things that we will learn next week when we do integration by parts. Um, so one thing that you should notice is that like all the integration that we do now, we haven't done a lot of weird integration. Gosh, have I even done something that's not a polynomial in the last week here? It's sort of expected that we can go backwards and forwards, derivatives, integrals with like all of our families of functions, right? So we've done some rational functions and gotten out some natural logs. We've done some polynomials and those have been pretty easy. We've done some exponentials. Exponentials always result in more exponentials. Trig functions always result in more trig functions. But there's one that we haven't done yet. And it's weird because it seems like it should be easy, but I can assure you that at no point in Calc 1 did you ever take the derivative of something and get your answer to be the natural log of x. So one of these small bonuses that we get out of the huge concept that is section 7.1 next week is we're going to be able to fill in a couple of gaps for a couple of basic functions that we don't currently know how to integrate. So integration by parts is section 7.1, and again, it's one of the most important tools in your tool bag. If we're building a house, then this is either a saw or a hammer. It's like you couldn't do it without it. It's one of our most important techniques here. So again, next week, 6.5, easiest section of the whole class. 7.1, definitely not the hardest section of the whole class, but man, like if I'm seeing a person come out of Calc 2 and I want to double check that they actually know the things that they were supposed to know, and if I got to pick 3 questions to ask them, one of them would be an integration by parts question associated with 7.1. So it's a very important tool in our integration toolkit. And we'll get that there in 7.1. So, and also, okay, actual last comment for the day. Remember that our layout of this course is sort of like chapter 5 was introduction to integration. Chapter 6, applications of integration, which we saw was basically volume computations and physics. Chapter 7 is going to be advanced integration techniques, and I want to put that in quotes because there's about a billion integration techniques that are more advanced than the ones that we're going to get, but these are a step up from just like basics like U sub and stuff like that. And then chapter 8 will again be applications. I am very much looking forward to probability. That's my favorite section maybe to cover here. And then we'll get, isn't it 9 is our diffie-q, and then 10 is 10 and 11 sequences series, something like that. So we kind of just do this alternating back and forth. Build some tools, use them. Build some tools, use them. And so we're going back into a tool building chapter next week, and there's some super cool tools that we're going to build in there. A lot of our integrals, we're going to get integrals of inverse functions, integrals of inverse trig functions, integrals of kind of filling in all the story, all the stuff that you can take derivatives of but don't know how to take integrals of. We're going to get most of all of that in chapter 7 here with some extra good techniques. So stay in contact with me. I've had a bunch of people ask me some really good questions about things. I'm going to keep giving good anytime that it's reasonable. When people come to office hours and ask me questions, I'm going to keep on posting the documents that I make in office hours in Canvas so that you can see the homework help that I gave to people. Keep working with people. I attempted for like the 100th time. This Discord link is like the worst thing that's happened to me this semester. I think I've maybe fixed it, but I've even already heard that maybe not. But in any event, I did post the Discord information in a more accessible place. If you haven't joined the class Discord, I would strongly encourage you to do that and to work together with people on all of these things, because this class is hard and you shouldn't do it alone. So join the class Discord, chat it up with your classmates, come hit me up in office hours tomorrow and Friday, and we'll keep moving along here. Happy week 3, everybody. I hope the sky calms down. I hope the fire calms down, and I will see you guys either in office hours or at the next video on Monday here for a little bit of average value on Monday. Have a good one, everybody. I'll see you guys then.